Buenas tardes. Hola, muchachos. Our next speaker is also from America and also from North America. So, so Elmar Wagner, originally from Leipzig, right? And I understand that your talk was prepared some luxurious lunch at business class lunch at Berlin Hauptbahnhof.
Well, we have business lunch and
exactly. So top quality slides from a top quality speaker. Elmar, we are delighted to have you around. The floor is yours. Take it away. Compact quantum surfaces. It's all yours.
Thank you. It's a bit less about half-Cstar keepers, but this is part of the project of Ale, which has problems with arriving. But we started this with Hong Szymanski's paper. The idea was I gave him this project to study non-convex complexes. And we started on the paper, looked at the graphs, so we looked at the edges which we have to erase to get balls, spheres, and then to clue them. But then the people in the audience, or there are many people in the audience, that were a bit faster and they started to publish. So what is left our project, we still have the project, which we can maybe see, well, we see it here in an example where it works. So the idea was to give conditions when our CV complexes maintains the topological invariant. So find some conditions that guarantee it. It works in the quantum, in the case of quantum surfaces, and that was actually intended as the first induction step. So if you want you construct CV complexes, what we wanted to have is step by step we guarantee that have same K-series. So if we know that the x minus n minus 1 skeleton has the same K-series, we attach cells and we maintain. This would be the induction step, but also the base, the first step. And what we also see, what it was Thomas mentioned, K-series is very rough for classifying quantum spaces, and that we will see here in the example. So in the classical case, well, you have different arrangements to construct them. In the quantum case, we get non-isomorphic Stahlschiebers. What you see, also to prove our isomorphism, our classification, I will use PDF theory found by Fillmore. It's interesting because that is actually the starting point of KK theory. Someone in the audience, some students want to learn KK theory. I really I recommend to start really with PDF theory, with the Stahlschieber extension. When you have the Stahlschieber extension, you have on the left side you have algebra, you put in the right side, and that is the Kasparov's invariant functor. So that's how KK theory started. Now in our case, since we are in 2 dimensions, so the 6-term exact sequence is enough to determine K theory. It's simple. Everybody has a bit experience can do it. But as I say, that was only the motivation example for higher TV complexes, and a way to assemble all these. So if you go higher and higher, you have to iterate 6-term exact sequence. You can make Meyer Vietoris. So a theoretical way to assemble this is to study spectral sequences. The problem is why we didn't get the result as expected is distortion. As soon as distortion appears, so these spectral sequences compute typically the homology of the graded object, and then to reconstruct the homology of the filtered object, you have face some extension problems, and whenever torsion appears, well, that's difficult. But it was not so much that we want to compute it, we want to give conditions so that's a classical, we can compare it with a classical with classical K-theory. But we have to deal with distortion. That's not finished. Anybody that wants to join us, very welcome. So let's go for the Cstar, half-Cstar conference. There should be at least one. So here's the one that I will use. It's a Topless algebra, and it's not completely trivial to show that this is a Topless algebra. So one really has to work a little bit with the representations and the universal Cstar algebra.
Elmar, may I jump in, because this is something very interesting. Its part is an extremely this isomorphism you're talking about, because let's think about the Topless algebra not as Topless but as Coburn. Okay, so the universal Cstar algebra of just one isometry. Okay.
Yeah.
And then well, this is different set of generators and relations. Okay, exactly. This is what you wrote.
Yeah.
And but this is part of a general theorem. You see, when you define graph algebras, you have Coons-Krieger relations of the first type and on the second type.
Yeah.
And if you divide just by the first type, so you know S E star SF is Kroneker's delta EF projection at E. That's the first type relation, okay? And if it and if you divide only by this, these are so-called Kohn algebras, C-O-H-N, not Alan Kohn, C-O-H-N, Kohn algebras. But there is a theorem that tells you that every Kohn algebra is a Leavitt path algebra for a transformed graph. And you can think, if you just use one isometry, this is exactly Kohn path algebra, because you have just one relation, S star S equals to 1. You draw a circle. So when the Topless algebra has a graph which is a circle, so when you have just one Coons-Krieger relation, the first type Coons-Krieger relation, then the graph producing you the Topless algebra would be just a circle, yeah, because you would have simply one relation, S star S equals to 1. Yeah. Okay. But there's this general theorem that says that absolutely every Kohn path algebra is Leavitt path algebra for a transformed graph. There is a nice recipe, and it's completely universal. It works for all graphs. And in particular, if you apply it to the circle graph, you get this Topless. And then when I say Leavitt path algebra, this is like a Hopf algebra of a compact quantum group Cstar algebra. This is nice, dense part, which sits inside graph Cstar algebra. I mean, if you want, graph Cstar algebras are universal completions of Leavitt path algebras, and I think it's worthwhile to emphasize this is a general phenomenon, and it's a very nice theory. I proved it in my class. It was enjoyable.
Okay, do you have notes?
Well, it's in a book. I mean, I took it from a book.
So yeah, that explains the slide better than I can do it. So I can go ahead, because I like a different representation of the Topless algebra, which it's automatically we see that it's a quantization of the continuous function on a disk. So it goes directly to the Topless operators. We take L2, there's with a Lebesgue measure, then the analytic functions, square analytic functions are a closed subset, so closed subspace. Then we have projections on those analytic functions, and what we do is take a continuous function, and the Topless operator is given by multiplying the C's analytic function by a continuous function. This is not analytic anymore, but we can then project in the Bergman space. And this is a Topless. These are the Topless operator. And the Topless algebra is an algebra generated by all these Topless operators. Here we have generators. So if you take the identity map on the disk, and consider the corresponding Topless operators, since the identity map generates by Weierstrass the continuous functions on the circle, these are generators of the Topless algebra. And from there, many theorems can be proven just by looking at the generators. For example, that all these operators, the commutators, are compact. So it's up to compact, it's a commutative Cstar algebra, and it also tells us that we have all these Topless operators are essentially normal. That way I will use in the following. So here's the Topless extension. Here we have it's very well-known, very famous symbol map. And if you want to understand why the symbol map gives a circle, so we have the I took it as a definition that the compacts, generators with compacts are inside the Topless algebra. It's a closed ideal. You can divide it. And then the question is, what is the image in the Kalkin algebra? And if you look at the generator, it becomes a unitary generator of the commutative algebra. And the only thing is you have to check what's the spectrum. So it's a unitary, there's a spectrum on the circle, but its lift has a index. So it cannot be lifted by a unitary. And that tells you the spectrum cannot have holes on the circle. So it's a whole circle. And that means here we have in the quotient is CS1. And this allows us to look at the Topless extension as the symbol map is a restriction of functions on the circle. The algebra is non-commutative, but we have a commutative boundary. And as I said, I wanted to study CV complexes. Yeah, we can clue boundary on one skeletons. And in the case we take these Topless operators as functions on the closed disk, this is really the restriction of the function on the circle. So that goes very well with interpretation that the Topless algebra is a quantum disk. And if you look at the classical picture, what we did is these continuous functions on the open disk that mention infinity we replaced by the compact. So it's slightly non-commutative. Now I wanted to define the closed quantum surfaces. We start with the orientable case. What we do is, if you look any book on algebraic topology, you see that there are polygons, and then you assign arcs. And these arcs you have to glue, and then you get some space that is homomorphic to your chosen closed surface. So what I want, the polygon, we can take the circle. There's no problem with this boundary. And here I have some assignment of arcs. This looks like the normal form that are usually in the books. But the only thing which I want, we don't, in the moment we defined, we don't know if all these Cstar algebra, we change the arrangement. If we get isomorphic Cstar algebra, we don't know. I allow any arrangement so that the quotient in the classical case does give a classical closed orientable surface. So what I don't want, for example, you have a 1 and a -1 shouldn't be together. So if they are together, you can just close them and then one arc is eliminated. These things I don't allow. I want that any arrangement is allowed so that we get in the classical case a surface. And then it's quite obvious how I can define the closed quantum surfaces. I take elements into Topless algebra, I apply the symbol map, so that means the restriction on the boundary, and then I want to identify points, which means the Cstar algebra doesn't separate these points. They have the same value. So any element from the Topless algebra which satisfies these boundary conditions defines for me the subalgebra in Topless that defines a closed orientable quantum surface. In this case, depending on the arrangement, this is a orientable case. So here we see what we did, what I already mentioned. It looks like these interior we just replaced by compact operators. When you see it also on these Cstar algebra extensions. So my objective was always to construct something which preserves the topological invariance in terms of case theory. Then we should have to obtain such a thing. Well, these compact operators should relate to the inside of a disk of an open disk, and this is quite natural, which gives us the hope that everything will work. So the disk we can take as we can replace the disk by an interval or by R2, which means we take the double suspension of the complex numbers. Well, what periodicity, this is case theory of 1 point, but then we stabilize it. Case theory is stable, we stabilize it by the compact. So that means, the compacts in a very simple way have the same case theory as inside of the disk. So that gives us the hope that we really can do something which maintains the topological invariance. In the case of non-orientable quantum surface, we have to be a bit more careful, because we will see later that we obtain non-isomorphic Cstar algebras. So if you take a number of connected sum of 2 tori and connect it with some numbers, 1 is enough of the projected space, you get always something non-orientable. Here in the quantum case, we have to distinguish. So we take two arcs on the surface. The first one corresponds to some projective space. So the K connected sum. So if we shrink these that correspond to the torus, this one will give a the connected sum of K projective spaces. If we shrink the first ones, the last ones give us the connected sum of tori. Again, the order doesn't matter. We will see later that is isomorphic. I just require shrinking the source that come with the inverse orientation. Shrinking them gives the connected sum of projective spaces. Shrinking source that have twice the same orientation gives the tori, some connected sum of tori. And then the definition is the same. We take subalgebra of the Topless algebra, we apply the symbol map, and what's written here is they should obey these boundary conditions, which are given by identifying arcs. And again, the inside we didn't touch, so the inside are the compact operators. Now, in the classical case, when you look at the book, you need to, the proof goes with giving some algorithm to cut through the inside and then glue in a different way. Well, since this one is in simple algebra, we cannot cut into compacts. This technique does not apply, but we are talking about Cstar algebra extension of a commutative Cstar algebra by the compact. And this is very well studied. This was a starting point. So our generator, we can find a generator which is essentially normal. And these generators are classified up to unitary equivalence by Brown-Douglas Filmer theory, which was the starting point of KK theory. And that's we use for our classification. Now, before this talk, there was a discussion about that our Cstar algebra extensions can be written as a pullback. And that is what started our, with Ali, our idea to make CV complexes. Now, the Busby invariant, what you do to find the Busby invariant, we have here the algebra, which is the quotient of those. Now, since it's surjective, any element can be lifted to the middle Cstar algebra. This lift is not in, it's usually it's in homomorphism, is the extension is considered trivial, which we don't want. But since this ideal sits inside, the middle Cstar algebra we can view as a subalgebra of the multiplier algebra. And then we quotient out. In our case, we have the compacts. We take the multiplier algebra, quotient out, and this becomes a homomorphism. This becomes the Cstar homomorphism, which is convenient because now this element, this algebra, which we considered as a subalgebra of the Kalkin algebra, can be anything. Can be any Cstar algebra which is isomorphic to a wedge product of circles. We do in both cases the same procedure. And in our case, since we talk about Topless operator, we can give a very concrete description of the Busby invariant. We take a function, which is, well, we have these are the boundary conditions. Here is missing, C is missing. Now we take the quotient of the circle by our boundary conditions, and this quotient we pull back, so get functions on the circle. We lift it to a Topless operator. That's here. We take the functions, take the pullback. We define a function on a circle. We extend it by just multiplying with the radius. It gives it a continuous function. Then we take the Topless operator. And the nice thing is, and then we have to take the quotient, with a symbol map. So the Busby invariant is then the restriction of the pullback functions on the circle. Very easy to define. And from the theory of the Cstar algebra extension, automatically we get an isomorphism as a pullback of the Cstar algebra. Here's a multiplier of our ideal. We take the quotient of the multiplier. This is a Corona algebra. That is a Busby invariant that maps our Cstar algebra. We extend by the compacts. In our case, maps into this multiplier algebra. And then the pullback, this pullback is isomorphic to our middle term. Yes, it's completely determined by the Busby invariant. Now, here, we know that our Busby invariant goes to the circle. And the Topless algebra maps surjectively to the circle. So we can replace this bounded operator by the Topless operator without changing our Cstar algebra. Take the pullback diagram and have a pullback diagram where we have a circle, and here we have one skeleton, and our Busby invariant, which we can identify with this pullback, tells us how to clue the boundary of this disks on one skeleton. So this gives us the interpretation of CV complexes, and it's obvious whenever we can have something like, we can map, we have something like what we call balls. We have heard it in Francesco's talk. Yeah, we need a ball which has triple K theory because it's constructible. We have something we can consider the inside. The quotient is a sphere, which we see has a K theory of the sphere, and then finding such maps give us a description of cluing disks or higher disk or higher dimension to some skeleton. And the classical case is given by these push-out diagrams here. This is just the inclusion. Here's where all these complicated structure comes in. So this tells us which is the dualist Busby invariant. Then how do we clue the boundary of the disk on the one skeleton? It's in the projective space. It's different than here. So these maps store all the information that tell us what is our surface. It's in these cluing maps. And here's just so this becomes a push-out diagram. You dualize, and this is this pullback diagram obtained from the Busby invariant. So now to study isomorphism classes, well, if we compute the K theory, we know that the torus and projector spaces can't be isomorphic. But it's in the moment it's not so important. We take two of these Cstar algebras. These can be different Cstar algebras of a Topless algebra. So if you take the same object, like it's the same quantum surface, the same genius, but we can have different arrangements. And the question is, if we have different arrangements, can we prove that they are isomorphic? That's what we expected. And we have to be careful because some arrangements in the projective spaces, they look quite different because of these directed sums. Now, the compact operators is a Jacobson ideal. It's a intersection of all ideals. And therefore, when we have a completely abstract isomorphism, we get an isomorphism between the compact operators. Now, any isomorphism of compact operators can be implemented by a unitary in the space of bounded operators. You just choose in each case for in each case a vector, and then the compact operators generate the whole Hilbert space. Well, and then you just identify the operators acting on one single vectors. And that's the way that you construct your unitary operation, your unitary operator, and then the automorphism is given by conjugation with a unitary operator. Once we have an automorphism on the ideal, we can extend it in a unique way to an automorphism of the multiplier algebra, which are all bounded operators. So any of these automorphisms is given by conjugation with a unitary operator. Now our generators are essentially normal operators. So what we are talking about is when we have a isomorphism of these style algebras, when we look at the generators, we get unitary equivalence of essentially normal operator. So Brown, Douglas, Filmore were just asking this question: when can two essential normal operators with the same essential spectrum be unitary equivalent? And that answers these questions. So the answer of these questions, PDF theory, is exactly the answer: when are two of our quantum surfaces isomorphic? So, and it's known that the classification goes by K1 of the central spectrum. This was a very celebrated result because something from algebraic topology, the invariance of some compact set in the complex numbers, give us information about when are essential normal operators unitarily equivalent. So in the Topless algebra, we have even something more. We know that PDF gives the classification by indices of the generators. And in the case of the Topless algebra, we know that our functions are defined on a circle. So the index relates to the winding number, actually with with minus winding number. That's not so important. So for our examples, if we take orientable surface, then each arc appears with its inverse. So all winding numbers are 0. In the case of the non-oriented case, we had here the connected sum of k projective spaces. So each arc occurs twice with the same operation. So we have here an index in the first k elements, we get an index 2. That's different. And now you can see, you can guess already which algebras are isomorphic. And here's the theory. So apart from demonstrating which these algebras are isomorphic, we can give a very explicit description. So our circles, we realize as a, where best I actually picture. Something seems to be missing. Well, maybe it comes later. Yeah, that's what I was looking. So we realize it as there's a central spectrum we realize as a Hawaiian earring. And so there's a compact subset of the complex numbers. Now we have K theory. So these essential normal generators are classified by its K theory of the map that maps from the circle to this Hawaiian earring, and U is a Fredholm operator with index 0, where triple 1. So to get these circles, we take the radius j plus 1 j with center minus 1 over j, and then all these circles have a common point 1. So the essential spectrum is these circles. These indices are 0. So any arrangement that you can make, and even what's the theorem, this doesn't matter even if the result gives a topological manifold. Any arrangement you make with this number of arcs, each arc starts and ends on the same point, so they have a connected sum of circles, are isomorphic to this algebra generated by the compacts and this essentially normal operator. With U, the taken as a bilinear shift. Now, in the case of the connected sum of projective spaces, so we have these first arcs that appear twice, that have binding number twice. So the operator, the Fredholm operator, corresponding operator, Fredholm operator should have index 2. Well, it can have minus. If it has minus 2, we just take as a generator that joint. So I choose here the shift. So the shift has its essential spectrum is a circle. Here again, I take the radius j plus 1 divided by j, in the center 1 minus j. So the essential spectrum of these are circles which are connected in one. The ones that have zero, I take again this bilateral shift with the same, yeah, continuing with this radius and the center. So all these algebras, subalgebras of the Topless algebras are generated as isomorphic. So this algebra which is generated by these quite simple operators, shift and unity, this unitary operator. And the proof is just, yeah, it's what I mentioned. Winding number zeros, we take use. Winding number 2, we take the shift operator. And in case you are worrying about the orientation or the order of these arcs, well, we just take these Hawaiian earring, then we can flip circles to get the orientation we want, and we can rearrange them. That's no problem. So all these operators, so our compact or closed quantum surface are generated by these essential normal operators. So K-theory, it's simple here because one 6-term exact sequence is enough because we really in dimension 2. So if you look at the construction of the one skeleton, well, that's simple. So the K-theory it's easy to calculate. We have one point, so we can look at this connected sum of circles as a one-point compactification of open intervals. So you have direct sum. So the K-theory is just, so K1 here is just one generator with winding number 1 in each interval. So K1 has the number of copies of interval of the open interval. EK0 of the one skeleton, well, we have only one generator. It's a trivial one. It's comes from the identity map. So if you here's the index map. It's called index map for a reason, and we are in a Topless algebra. Our quotient lives in the Kalkin algebra, and this index map is really the Fredholm index of the lifted element. So we have an element in the wedge product of circle. We lift it to the Cstar algebra. Well, we have to double it and then to lift it, but then it becomes really the index map is the index of the corresponding Fredholm operator, because we are working in the Kalkin algebra. So we know how this map. We don't really need to define, yeah, to use generators explicit description. We know it relates to the winding number of the functions on the turtle. So if you have a look at it in the first case, in the oriented case, well, this way a winding number 0, this index map is 0. We get here an isomorphism. So we know that K1 is the number of circles. And here we get an exact sequence, but that part is split because it's just here one, we can map 1 to 1. And this remains as a direct summand. So K0 of the oriented surfaces, quantum surfaces, are Z2, exactly as in the classical case. Here we have this Z to the number of circles. That's again, it's equal to the classical case. So it's the K-theory of the compacts. Of course, it's very simple. We can take just the projections of with a certain rank. But I always like it, the idea to represent them as some sort of a pot projection, which again tells us we really are deforming a disk. So we can take these elements UN, we can take it as a 1-by-1 matrix, the unitary element. We extend it by multiplying with the radius to the whole disk, takes the Topless operator, and then the index map here gives exactly such these, well, I call them spot projections because they're really very close to the spot projections on a disk. And to live in the ideal, we have just to take spot projection minus its rank, and then we have generators, which look, yeah, pretty complicated if you think about complex with just projections on a one-dimensional space as a generator. Now, in the case of the non-orientable quantum surfaces, something changes. The index map isn't 0 anymore. So the last part, we had arcs that appear with its inverse orientation. This is still 0, but here any arc appears twice. So if we map it into, well, if we lift it to a Fredholm operator and compute its index, it becomes twice its the winding number of one arc. So the first k elements are multiplied by 2 and sum up. So our image is 2z, and taking the quotient produces these summand z2. This set comes here from the splitting. So it's these are the trivial projections, and that's the same as in the classical case where these projective spaces have k0 z plus z2. For k1, you see here this image is a copy of z. So the kernel takes just one. Yeah, the kernel is one-dimensional, and it reduces as n to n minus 1. And again, it's the same. It's the same as in the classical case, because to have at least one of these has to be non-zero. So we have at least one element that doubles. And if you want to look at the generator of the distortion part, well, if you take here the element with winding number 2, it's same in the classical projective space. If you take a loop and go twice, it's trivial. So they can be deformed to constant function. Well, that is a homotopy. These actually we can do here in the quantum projective space as well. So taking twice becomes 0. This element is already 0, and it's twice the spot projection minus its rank. This is distortion element. So, and then comes what we tried really to generalize in the step-by-step for higher dimensions. So it should work. For truth is the first example where we have clearly something non-commutative. I don't know if someone has a non-commutative version of an interval. Never heard about it. So we have seen this kind of pullback we have seen. Now we can have in our case, our one skeleton was just a wedge product of circles. So we can, of course, copy many copies of the quantum disk on the circles. So if you quotient out the inside just by the compacts, we get classical commutative Cstar cheapers. Oh yeah, here's again mistake. So we take copies of the continuous functions on the boundary. So this is just taking the quotient map. Now all the information, how we clue and how non-trivial is our cluing, is in this map here called Rho2, which was in the before we identified it as a Busby invariant. So the things which make K-theory non-trivial, it's all the information sits here. Now to have a CV complex, well, that's the one skeleton is our wedge product of circles. Well, we take a point here and intervals, and then we glue all these intervals, the endpoints. So its boundary are 2 points, and then you see also here we have one choice, a point we can just map in the copies of alphas in each one, same value. So these 2 points are get identified. Any 2 points get identified with alpha. They don't separate anymore. In the style shapers, they don't separate all these points. So all these points are glued on one point, and this gives our one skeleton. For zero skeleton, it's completely trivial. We have one skeleton, and then from this one skeleton, which is here, which is classical, we get to the 2 skeleton, and then we would like to get higher and higher and higher. So the question is, where's the information that guarantees that we have that we remain with the classical K-theory? Now here, these are spheres. You can even think about higher dimension. We have a copy of spheres. Each one has one generator. It depends on the even or odd part. So in the even part, we have one non-trivial generator. One trivial generator is one, and one non-trivial that comes from sort of spot projections. So this one are supposed, if you think about higher dimensions, so we assume that we know this K-theory. Well, we know it we assume that's the K-theory. Well, we don't need to know it. We assume that this K-theory is the same as the classical case. So sure, if it's commutative, there's no problem. Now, this map, here we can identify generators. What we want is, so we assume that this map, as in the classical case, maybe after a permutation, that maps these elements, the K-theory, which is equal to classical. So these generators maps in certain generators in the same way as in the classical case. And then we want to prove that our last step of our pullback diagram, or gluing these n disks on a n-1 skeleton, that we want to prove that this one has the same K-theory. So the idea was to use spectral sequences which work quite well. So that this spectral sequence organize all our information. So the first thing we start is, we see that this is a AB morphism, surjective, because it's just the quotient. Now, if this one is surjective, that means anything that lands here has a lift. So that makes this map, these projections, it's just the projections on the second component from the n-1 skeleton is surjective. And here it's always, so which corresponds to the classical case. Of course, if you take an n-1 skeleton and then glue something, so the n-1 sits inside the space as a closed, even in this case as a compact subset. So you just project down to each skeleton. I've just put it for our case n equal 2. But from each skeleton we project down and to the next one, and we stop 0. What we want, the filtration which we consider, so that's our sequence of projection, also to project down. So we can use this one as a restriction of the skeleton of dimension 1 less. Now, the filtration comes from considering the kernels. So you start with 1, there's a kernel. And you see already the last one is always very nice. Yeah, the kernel is taking out x, the last x, so the n-1 skeleton. If you take it out, you're left with the open disks. And these are very nice spaces, and K-theory is known. And the other ones, other algebras are not so nice. But anyway, what we need in the spectral sequence are quotients. That makes it nice. So here we have these ideals. We add more and more morphisms. So these ideals become bigger. We start with just by what makes the formula nice, and a-1 we set 0. Now here, this is a filtration of ideals. And apart from our A0s, the other ones here get more and more complicated. But if you take the quotients, oh yeah, that's just have a look at what it means classically. I put a Q, but set Q equal to 1. So 0 means 0. The empty set, right? Now we take out the if n minus 1 means we get to this, and then we get, well, we take smaller and smaller skeletons out until we have the last one is taking the empty set out, so we recover our Cstar part. The quotients are the interesting part. So taking the quotient here is obvious. I mentioned it twice already. Now, if you look at the quotient here, so if you look, A0 is this one. So X1 is completely removed. And then we remove from the part of X1, we remove X0, which is a boundary of the X1. So if you take the quotient, what we are left is with the disks of a lower dimension. So we have here we have 2 disks. We have the 1 disk, and then here we have 0 disk, which is just point. So the disks is, well, this is what we clue step by step. Now, the first thing is, it's very nice that the K-series is known. I already ordered it in the way we would write the spectral sequence. I haven't had the time to look up and how to implement it in LaTeX. But what you can see here is I already ordered it. Well, that as one would order the E1 page in a spectral sequence. Schochet has a paper where topological, so he really had some topological motivation, but he said, okay, we have filtration of ideals, we can compute spectral sequences. So we have this one K1 of 2 disk 0. K0 of 1 disk open interval is 0. And then K1 of points is 0. In this line, we have only zeros. Now here, this is just the copies of this. We can start with n0 points. We clue on these points n1 intervals. And then on this one skeleton, we may clue n2 disks. So here we just have this count just the numbers of balls that we are cluing to our skeletons. Now, the first thing and the most important thing is to find this differential. So in our spectral sequence, so this is a page. If you know spectral sequences, this is the first page. Now we have this differentials goes in this direction. This would the E1 goes from lower to higher and higher dimensions. These differentials are the dualizations of the boundary maps. So if you want to compute the homology of a CW complex, you have this homology. You have this boundary maps. This boundary maps the boundary of some disk maps in a skeleton, which can have quite complicated K-theory, but it maps in some generators. And the dualization of this is these maps the first differential. You can see it if you look. So at CST1, it's a differential is way explicit. We can describe it. So we have this means the connecting homomorphism. So it goes from the connecting homomorphism goes from the quotient by some here it's A1, HA. It goes to the case, so from K0 to K1. If you look at the spectral sequence, this is the boundary maps of the 6-term exact sequence. It goes from A1, 0 K0 of A1, so from the quotient to K0 of K1 of A1, and then we don't want to have exact sequences. From A1 we go straight to the next quotient. Yeah, we have A1 and then we go to the equation A0. And the same is here. From K1, from the quotient, we go to K0 of A0, and then take the quotient. This is not exact anymore, but this is exactly what these are, the dualization of boundary maps. And P is just going down in again to the disk, so the interior. So in what we did really, what we observed is that this D1 between in the spectral regions is really comes from the Busby invariant. So the Busby invariant, I don't know if you go back. We can look at here. So I say that this is Busby invariant. So this tells us how do we clue. Now, if you look here, the K theory, this is not, these are, is a quotient by these open disks. So we have spheres, a couple of spheres, and we know the K theory. So these are elements, complicated elements in some K theory. We can really think about higher, it will work. It's just the same. And then there's this one from a n-1 skeleton. It identifies some generators with some generators here. So to have to say we're constructing something which is classical corresponds to spheres, story, or something more complicated, you say that must be the same. Otherwise, it doesn't make sense that we are constructing a sphere or a story if this one doesn't match with the generators here. So this one should be the classical part. And in our simple case, no, where is it? Yeah, that's the last page. Right. So I haven't had this time. So our differential, we can relate to a mapping which we expect the same to be in classical. So here it's once we have this, just writing down the spectral sequence says, okay, we have the same E1 page as in the classical case. And if you work with spectral sequences, the most applications that I found was A2 is stationary, and then we can say about something about our cohomology. A2 is stationary because if we so the D1 goes 1 to the left, the D2 would go twice to the left and 1 up, but it hits always a 0. So when we have a spectral sequence which is short like this, actually these points never matter much. So these points we can treat. We know what happens with points. We can shrink to our skeletons until we get only 1 point. But once we get this D2 is already 0 and D3 goes out. So that finishes our spectral sequence. E2 is a cohomology. So this differential D2 is E1 squared is 0. We compute the cohomology. This cohomology now gives the A2 page, and to find the K1, we go from this and this, a direct sum. But since this one comes from points, it's always zeta. So we have copies of zeta. We have the free zeta module, and so from the graded, from the groups of the graded algebra, we can reconstruct the groups for the filtered algebra. And for K1, it's just one component. So this is a diagonal that it goes with K1, which we computed. So the homology with the 0. So the homology on this place gives us automatically K1 of our quantum surface. And the idea was to do this in higher dimensions, but in higher dimensions we cannot assume, and it will not be the case that it stops at E2. Then we have to compare the higher differentials with the classical. We don't. Yeah, we will always have the problem if there's torsion. We cannot reconstruct from the abelian groups of the created object, we cannot get to the filtered object. There will always be a problem, but we would like to see, okay, we have the same generators, the same elements. We wanted to identify generators. So it means basically when we take tensor product of disks, if something is trivial, we can extend it to the center. If it's not trivial, there's no way to extend it to the center because it's from the boundary to the center. So, but E2 starts to be complicated. The problem is the theory tells us there is an element that comes from a lower. So these are the bound. This here is obviously it's classical the boundary map. But then we can have elements that come from in K-theory that come from lower dimensions. And the problem is this existence. We could not express it completely constructively to compare it with some classical construction. That's where we failed. So anybody in the audience is invited to participate in our project. Well, time is running out, not for my talk, also for Ale. So yeah, it's still some work to do, and it's a complicated part that we have to do. So I finish here. Thank you for your attention.
Muchas gracias.
De nada.
Questions, please. Just grab the mic.
Thank you. Thanks, Elmar, for a nice talk. I might accept your invitation at some point.
Great.
Because I was doing the same kind of calculations for RP2Q, the same spectral sequence calculations some years ago. It's a pity we never talked about it. But okay, so because Chauchet, first like a comment or more of a remark. So I think Chauchet's inspiration for this paper, he wrote a series of papers about axiomatic cohomology for Cstar algebras, because we all know that there's no theory for like cohomology for Cstar algebras. And I was thinking about CW complexes. And I think that what you're doing here might be a version of cellular cohomology, right? It is, right? It is the same, you get the same groups, right?
No, that's already is a problem. If you mentioned, since you mentioned the projector spaces, if you compute the homology with the cell complexes, they are different. If they are torsion, they are different. So K-theory differs from the cellular homology.
Oh, yes, I know. But if you look at cellular cohomology of classical spaces,
yes,
right? And then you look at what you get here.
Compare.
Yeah.
That's the idea. Exactly.
Yeah.
Very good.
Yes, yeah, so I had this same idea, and this might work, I know, to do more general things.
Yeah,
right?
What I mean happens if something is, well, if you look at the cohomology, you want to know the kernel. When is something zero? If you can extend it inside. So it puts a condition on our Cstar algebra, which we consider core. You need something which we say you have a generator on the boundary. If that one is trivial in K-theory, we can extend it. In the classical case, so that was our idea, that we identify the same procedure. Something is trivial, it can be extended in the inside.
Okay, and what is interesting for me, example, maybe that would be interesting for Piotr as well, is that original proof of Borsuk-Ulam theorem goes through cohomology, right? Not K-theory.
Yeah.
And if we would have this cohomology, we could just mimic the proof that Makoto Yamashita has a proof of this Borsuk-Ulam theorem for Q-deformed spheres, but it's very technical and very hard. And the original proof just for homology, it's kind of not too technical. And if we could have some calculations, I know that for higher dimensional projective spaces, the E2 will not be stationary. It will be right, because the cohomology is like.
Then you get all this problem with torsion. You cannot reconstruct the proof. As it starts with RB4, it doesn't work for RB4. You can get only the created object, the groups associated with the created object. And we cannot reconstruct, but still, what I was hoping is I can identify generators. I can say, if something is trivial, if I can extend it in the cell, So we have something on the boundary where we clue it in generator, and then I can say it goes to the same generators. It has to be because when something is zero extent, you can do the same procedure. But yeah, to find that the problem is this. It's the existence. So there is an element that comes from the lower. And if you go higher differential, there's an element that is lower. But I have no explicit description of this element, which I can compare with the explicit element in the classical case.
Yeah, sure. I was getting the same problems.
Yeah.
Anyway, that's
Very good. Well, not
Yeah.
good, not good, but good, really.
so
Okay,
okay. Thank you.
organic.
That's
All right, anybody else?
So I have a question that I think I might have missed this part. So in your first examples with the one-dimensional, well, so with the surfaces,
Yeah.
right, where you're looking at certain identifications of arcs on the circle.
Yeah.
And all the Cstar algebras are subalgebras of the standard Topless algebra.
Yeah.
Just where the symbol respects the identification.
Yeah.
right? So is there an algebra that contains the higher dimensional examples in an analogous
Well,
way?
yeah, well, sure. I should tell you what are the balls. The balls are the tensor products of Topless algebra. This product of this,
Oh,
this.
okay.
And then for the odd dimension, we just added an interval. When we got what we started, this was all these examples from Szymanski on. We constructed in this way, all of them: projector spaces, field projector spaces, spheres. We were looking at what is a good ball. Then we can cut some edges from the graph, and then we get a ball. And then we said, oh, let's try it. If we can all these examples we constructed with doublets, and if we need something odd, we added an interval. It worked.
Okay, I see. Thank you.
Yeah, and this is the idea. Okay, we know exactly the balls. So these balls, we can in the Topless algebra. That is why I like this spot projections. There's a radius. This radius is we take there's these theta relation. So it's z star z minus q squared z star is equal to 1 minus q squared. This theta, this modulus of theta, we can replace as this r, and then we can extend things in the inside. That worked very well.
So when you speak about higher dimensional cases, you just take multi-quantum disks, right? So
Yeah,
these
yeah,
are
yeah.
your balls.
Yeah.
And when the sphere is just what? The boundary
It's
sphere.
just the quotient with inside. So
Yeah,
the
so
inside
this
is a
is-
compact.
That's exactly the Herod sphere.
Yeah. Actually, you should have stated. Yeah, right.
And then what? You do some boundary magic again? How do you proceed with it? What replaces these intervals? Or you?
The interval is the interval. We take this is this. and
Yeah,
then
but I'm talking about identifications. I mean, before your whole surgery was happening on the circle, right? I mean, the boundary sphere was just a circle.
yeah, well, this one. So we have the higher
You can
skeletons.
write. I mean, you can write on this.
Well, I can look for what I mean, but we have the skeletons here. So we call it x n minus 1, and then we need this one is a homomorphism that we can lift. Here is always it's a quotient, so it's projective. So we say any morphism is allowed. So whenever it's in this non-commutative, we have less possible homomorphism, but we allow here any morphism that's allowed. Of course, we want to have something which we call, which we want to compare with the classical CW complex.
Yeah, but that's still two-dimensional, right?
We go here n minus 1, and you take whatever you find. If this non-commutative is too much restriction, we don't care. Then they are little. Well, that's why we started with examples. So the Hong-Szymanski paper, we have all these examples of Hong-Szymanski we can construct in this way. So that is the motivation. This gives a nice set of examples and possibly more. Of course, since these are non-commutative non-commutative algebras. So maybe there are only a few possible morphisms. That's true. I'm not claiming that we get, yeah, well, we wanted also to get version for all. That's, well, one way is the commutative, in the last step, you make non-commutative, there's a commutative boundary. Then you can say, okay, we can construct, in theory, we can quantize any CV complex, but if you take commutative up to a certain part, and then the last step is non-commutative, it's very poor way of quantizing something, but it's possible. Of this we can do anything. Well, but we were more interested in this ball, discs, and an interval. How many are allowed? I'm not saying that. Well, I'm not claiming that in this case we can reconstruct any CV complex. Some, yes.
But you'd still do your surgery on sort of a classical subspace of your quantum space. All these identifications, gluing.
No.
No.
Well, if you go higher, not anymore.
Not anymore. Okay. So
These
that's
are not
good.
anymore, yeah, because we have, if you take two triplets, then the
Mhm.
product we have here on one is on a boundary. If you're once on a boundary on circle, we have the whole triplet algebra, and that's non-commutative. The boundary means really like in the classical case. So you have this product of disks, and then once you get on a boundary of a disk,
Mhm.
all the other disks remain non-commutative.
Okay. But are they somehow really taking part in the gluing procedure?
Yeah, well, if you like there's examples of Chemansky, we can reconstruct them, all of them.
Okay. Could you, for a second, go back to sort of the beginning when you had all these orientable and non-orientable surfaces? Yeah.
The definition?
Yeah, the definitions where you have these two families of yeah. Okay, so this is orientable, all right?
Yeah.
And just very naive, stupid question. So how are they related to graph-Cstar algebras? They are not graph-Cstar algebras.
Don't think so.
No. Okay.
Well, this is a sub-Cstar algebra of a graph algebra.
Yeah.
Right.
And because then when you go to these non-oriented, RP2Q is a graph-Cstar algebra.
RP2.
Yeah.
Well, maybe.
But is
Non-
RP2
Well, look at this. I mean, if you want to have graph-Cstar algebras, yes, they are.
Mhm.
Probably. Where is it? Our theory. So here, well, you have to check this. Well, this generator. So this is a graph-Cstar algebra, and this comes from a Cstar algebra. Graph-Cstar algebra. That's true. So that's a circle, and here we have chip, but it's a square chip.
Yeah, I mean, I cannot decipher it whether it is
It's,
graph.
yeah, it's if you ask me the question, I would look at this generator if I get it as a Cstar algebra.
No, but
These
just
have different, yes, these have different radius, so you can give n generators. I just, because for PDF theory, I wanted to have one generator. But this is an algebra which is generated by K squares and one bilateral shift, one unitary.
yeah, I'm asking because I know for a fact that for RP2,
Yeah.
this is a graph-Cstar algebra.
Well, but it's not RP2. Yeah, but RP2.
Well, one of them should be.
Yeah, RP2 is this one.
Exactly.
It's just this one, and then we take direct sums. It really looks like a very simple graph here with direct sums.
Because what it really is, you really have a Topless algebra. You have this boundary circle, and you have an antipodal map identifying points, and that's exactly our description of quantum RP2.
If it is a Cstar algebra, I guess it's a very simple one. Direct sum.
Well, the graph is a circle, and then two legs that are joined.
And then you have here one. You have copies of here. You have copies of unitary.
Well, I mean, when you look at the graph, this really comes from the quotient of a generic Podlesh quantum sphere.
Yeah, right.
Okay, you have a Z2 action, but not coming from the gauge action. So forget that Podlesh is a graph-Cstar algebra. Just take sort of the obvious antipodal Z2 action on the generic Podlesh quantum sphere.
Yeah.
And then obviously this will be the Topless Cstar algebra with the boundary points identified antipodally.
Right.
And that's, I believe, your construction. But when the graph is very simple, you take the graph of a podless sphere and identify the endpoints.
Ah, yeah.
So it's
Yeah,
two
yeah,
things, you have
yeah,
one
yeah.
thing. That's exactly our
Yeah.
graph Cstar algebra.
Right.
So this is why I'm asking this question. Okay.
Yeah. That's what I mean. That's what I mean here.
So
S
this will be
squared
graphs.
u,
Okay.
this-
Okay.
you have n minus k circles
Okay.
and
Really
so
disjoint, right?
yeah.
Oh.
And then is your Yeah.
Okay. Okay, interesting.
well, wait, no, there's a problem with the compacts. We have the whole compacts. If it would be the disjoint,
Yeah,
you
I
don't
somehow
have
find it
there's
strange.
one copy of the compact. You have only one copy of
Yeah.
compacts, but you have this disjoint union of the generator. So it's a bit tricky still.
But it's worth looking at,
Okay,
I suppose.
well, that's a good good task to learn graph algebra. But then I can give a graph algebra talk.
And then I understand. So you, from your pullback diagrams, you determine K theory of all these Cstar algebras that we defined, right?
In dimension 2.
In dimension 2, of course. And this includes generators.
What?
Generators.
Oh, yeah. Generators we have.
Yeah.
Well, generators.
Of the K groups.
Yeah. These are, yeah. We can get the generators from Cs. Yeah.
Mhm.
You can, yes. So what we can do is to get the generator, you have these arcs. Yeah, okay. Well, actually here. So the generators of K groups, what you take is, we have to take here, you have an arc, you take a unitary generator, and then you take the Topless operator and its modulus. So for
And now talking K0 or K1?
yeah, okay, K1 is easy because I gave the generators. It's the generators are really my plot projections, which are in the compact. But we have this relation. So the generators of K theory, it's one copy. We have one copy of compacts. We can take a one-dimensional projections, or we can take the my nice formula. That's simple. And for the K1 in the orientable case, well, you really take on one circle, you take unitary. You lift it, you lift it to some you need you lift it to that's we need to lift it to invertible with index 0, and that's in the case when we have these. Okay, the generators is you take one of these, and then you take on one circle. So there is on these n copies, which we have in the connected sum. We know there's one is in the kernel. So what to get something in the kernel is we take one copy of S squared, we take one copy of its adjoint, and then this one has index 0. So you take the compact operator 2 times 2 matrix, which makes this operator S squared S star. You make it unitary, and this one is a generator. So we can fix. You have to take always pairs. So you can take the first one as S star squared, and then you take in any copy, you take one of the S squared, make it unitary, it takes and that's it. That's our generators.
Okay. Just let me very quickly comment that one of the things that we looked at and did with Paul Baum was to show that this interesting non-trivial torsion generator of K0 of RP2Q is in fact the tautological line bundle.
Yeah,
So
that comes from
that
my what I call a spot projection.
Yeah, yeah.
Because it's a one-dimensional projection that rotates.
Yeah.
And then we can interpret them. Aha, that's in the classical case. It's just the projection in the it's the image. It's a line. That's a tautological line bond. Yeah, that's true. Works here as well.
Okay, any other questions? Okay, no. So let me see on Zoom.
No.
Oh, there's nobody on Zoom. No, Clayton. Yeah, okay. So I believe this is time to thank our speaker again. Thank you so much. Oh, wait, we have something in chat. Thanks.
Okay.
So not the question. So I let me just stop sharing, stop recording.